Imagine a world not too different from ours, but many times larger. A super-Earth teeming with untold geological wonders, orbiting its sun for billions of years. But then a cosmic drama unfolds, a slow, agonizing death. Its sun, once a stable star, begins to bloat, expand, and finally swallow its planetary child whole. The planet is gone, vaporized. But what if a faint echo, a lingering ghost, remained? What if we could still see the spectral residue of a world that no longer exists? For eons, this hypothetical super-Earth, perhaps 10 times the mass of our own, would have followed its predictable path. It might have been a crucible of extreme pressures and exotic materials, a planet unlike anything we truly know, yet fundamentally a world. Such planets are not rare. Exoplanet hunters have found many in our galaxy, but their fates over cosmic timescales are anything but certain. The life cycle of a star is a cosmic ballet of fusion and gravity. For stars like our Sun, the eventual fate is to become a red giant. They exhaust their core hydrogen, swell dramatically, and cool, transforming into immense luminous spheres that can easily engulf the orbits of inner planets. For a star slightly more massive, this process accelerates, becoming even more dramatic. As the star's outer layers expand, the planet's orbit decays. Tidal forces, immense gravitational tugs, begin to tear at the planet's very structure. Imagine the surface of this world, seismic tremors turning into apocalyptic quakes, oceans boiling, rock melting under the increasingly intense radiation. It wouldn't be a quick, clean vaporization, but a drawn-out, fiery descent into oblivion. The planet wouldn't simply vanish. Its material, iron, silicon, oxygen, carbon, would be ripped from its gravitational embrace. A vast plume of superheated gas and dust, the planetary corpse, would spiral inwards, like a colossal meteor shower dissolving into the sun's furnace. This influx of foreign matter, surely, would leave some kind of mark. Astronomers study stars not just by their light, but by their spectra. Light from a star, when split into its constituent colors, reveals a unique barcode of dark and bright lines. These lines are like fingerprints, telling us exactly what elements are present in a star's atmosphere, absorbing or emitting light at specific wavelengths. So if a planet's remnants were absorbed, might we see an anomalous fingerprint? The star's outer layers are not static. They're a churning convective soup, like boiling water. Any new material introduced would be mixed in, distributed throughout these outer envelopes. So the question isn't just if we'd see the elements, but how they'd appear, and for how long. Would they quickly sink to the core, or linger on the surface? Remarkably, astronomers have indeed found stars that exhibit peculiar elemental abundances, especially stars that appear metal-rich despite being old, or having an unusual ratio of certain heavy elements. For decades, these anomalies were often attributed to the star's formation history, or perhaps interactions with a passing interstellar cloud. But what if the explanation was far more dramatic? Imagine a star that at first glance seems perfectly normal for its age and type. But when astronomers take a closer look at its light, they find something subtly off. Not just a little more iron or magnesium, but perhaps an excess of elements like lithium, or even exotic elements that are typically rare in stellar atmospheres, but common in rocky planets. Planets, especially rocky super-Earths, have very different compositions from stars. Stars are mostly hydrogen and helium. Planets are rich in metals, everything heavier than helium. Iron, silicon, magnesium, oxygen. If a star had consumed a planet, we would expect to see an overabundance of these specific planetary building blocks in its atmosphere, above and beyond what its stellar birthright would suggest. But here's the strange part. When a star consumes a planet, the planet's material, though exotic, is still a tiny fraction of the star's total mass. It's like dropping a single sugar cube into an Olympic swimming pool. Would such a small amount of material really leave a detectable fingerprint? Or would it be diluted and mixed away too quickly to be seen? One theory suggests that the telltale signature wouldn't just be more of certain elements, but an imbalance. Planets often have volatile elements like water or methane frozen into their outer layers, and heavier elements concentrated in their cores. What if the star swallowed a partially stripped planet, or one with a very specific, unusual composition? Recent studies have focused on a particular class of stars, white dwarfs, which are the dense stellar corpses left after a star like our Sun dies. These star remnants often show atmospheres polluted with heavy elements like calcium, magnesium, and iron. For decades, the explanation was simple: asteroids or comets falling into the star. These white dwarfs, with their incredibly strong gravity, would pull in any stray debris, and we've seen evidence of this debris, shattered asteroids orbiting these dead stars. But what if this wasn't just small debris? What if some of these polluted white dwarfs were carrying the much more substantial spectral echo of an entire planet? The discovery of these polluted white dwarfs led astronomers to a more profound question. Did these stars once host entire planetary systems that have since been disrupted? And could the elements we detect be the final, lingering breath of a world that once thrived, now dissolved into the star that created it? The key is understanding the ghost signature. A planet's core is predominantly iron and nickel, its mantle silicate rock. If a star devours a planet, we wouldn't just expect an abundance of all heavy elements, but a specific ratio of these elements, mirroring the geological composition of the consumed world. That ratio is the fingerprint. However, there's a cosmic curveball. Stellar winds can blow lighter elements away, and some elements can sink faster than others due to gravity. So, even if a planet was consumed, the observed spectral signature might be skewed, an incomplete picture. This makes identifying a true planetary ghost incredibly challenging. But then, breakthroughs in spectroscopy and astrophysical modeling began to provide new insights. Researchers realized they needed to look for more than just heavy elements. They needed to look for ratios of elements that could only arise from the consumption of a planetary body, not just cosmic dust or smaller asteroids. And what they found, in some cases, was startling. Some white dwarfs show an excess of elements like iron and silicon, but also a depletion of more volatile elements like sodium or zinc. This specific chemical signature is precisely what you would expect if the star had consumed the core and mantle of a stripped-down rocky planet, after its lighter outer layers were already lost or vaporized. Imagine the scenario: a super-Earth orbiting a star that, over billions of years, slowly exhausts its fuel and becomes a white dwarf. During this process, the outer layers of the super-Earth could have been vaporized by the red giant phase, but the dense metallic core, a cosmic cannonball, could have remained, perhaps in an unstable orbit, only to finally plunge into the white dwarf's surface. This isn't just theory anymore. Through meticulous spectral analysis, astronomers have indeed observed specific white dwarfs with elemental compositions that closely match the expected makeup of rocky planetary cores. These are not random assortments of elements, but precise ratios that are alien to stellar atmospheres, yet perfectly align with the building blocks of planets. So the ghost of a planet swallowed by its sun isn't just a hypothetical tale. It's a cosmic reality we are now beginning to observe. We can't see the planet itself, of course. It's long gone, dissolved into superheated gas. But its spectral signature, a chemical echo, lingers in the star's atmosphere, a silent testament to a world that once was. Each polluted white dwarf becomes a cosmic tombstone, silently revealing the dramatic, violent end of an entire world. These are not just scientific curiosities, they are profound reminders of the impermanence of even the most massive structures in the universe, and the incredible, often violent life cycles of stars and planets. The discovery of these planetary ghosts opens up new avenues for understanding planet formation and destruction. It tells us that the universe is a far more dynamic and destructive place than we often imagine. Worlds are born, they thrive, and they die, sometimes in the most spectacular and tragic ways, leaving only a whisper of their existence. What if our own sun, in its distant red giant phase, eventually swallows Earth? Could future alien astronomers, billions of years from now, peer into our sun's dying embers and find the faint, ghostly signature of our world, a silent testament to everything we once were. A chilling thought, perhaps, but a profound possibility. What other lost worlds, consumed by their stars, are waiting for us to discover their echoes?